Bunny, say hello to the kids. Hello, kids. Hello. Oh, yeah. Hello. Okay, go back to sleep. Okay, so I'm going to do some notes for 7.1, or that interpreting change in exponential models. Some of you have emailed and said that you don't know what the heck is going on, so I'm going to try and make it as simple as possible. It's going to look like I'm doing something totally different, but I'm actually doing the same thing that they are doing. I'm just making it simple. So I might have some things that are not on that Khan Academy website, but it's just because I'm trying to make it better for you guys. Okay, so first off, when it comes to exponentials, there's like a parent function that looks like f of x equals a times b to the x. This is the parent function. Barney, shh. And a is the amount of whatever at the start. And b is the change to the amount over time. The change. Yeah, okay. And then x is the time. Yeah, duh. Okay, so when I talk about the change to the amount over time, you can either have something that grows or shrinks. Or another word for that is gains or loses. That's a slash right there. Or another word is increases or decreases. Or if we're talking about a number, the word grows, gains, increases is for a number bigger than 1. And decreases is for a number smaller than 1. Whoops, okay. And let's see, just a little side note right here. You hate these side notes, I know. If it says 1.65, like on this first example in Khan Academy, it has 1.85. That means that you're multiplying the last amount by 1.65 every time. And like this 1.65 is bigger than 1, so it's definitely going to grow, gain, or increase. And it's going to grow by a factor of 1.65. And when you're talking about percentages, this means that it has a gain of 65%. And you're probably wondering, what the function? Why is it 65% if I wrote 1.65? That 1 takes into account the original start amount. So it's this part after the decimal that you're looking at to figure out the percent, 65%. Or like, let's say we have, instead of in these parentheses 1.85, we have 0.25. That's smaller than 1, so that means a loss. Oh, poop. Okay, yeah, we lose. And it's not lose 25%. Like this one, the 65 was right here. The reason this was gain 65% is because 100% plus 65% is 165%. And as a decimal, we move the decimal twice to the left to make 1.65. So this one, when I lose, I'm not losing 25%. I'm losing 100% minus something to get that 25 left over. So 100 minus what gives us 25? And 100 minus 75% is 25%. So when I have 0.25, it's not that I'm losing 25%, it's that I'm losing 75%. If you didn't understand that, it's okay. I'm going to go over it more. I'll say it like 1,000 more times. Okay, let's look at this problem. It says, on the first day of spring, an entire field of flowering tree blossoms. The population of locusts, those are bugs, consuming these rapidly increases. That means the number in the parentheses is going to be bigger than 1 as the trees blossom. The relationship between the elapsed time, t, in days, so t is days, since the beginning of spring, and the total number of locusts, L of t, that's the bugs, locusts, is modeled by the following function. Okay, first let's figure out what all these numbers are. This 750 means there's 750 locusts at the beginning, at the start. And then every day, and I got day from the fact that t is in days, every day we see a gain or an increase